Okay, so on the top side of this part, we really have just a few features left. We've got these 6 holes for the wheel studs, and then we've got these however many quarter 20 tap features. First thing we're going to do is we are going to prep for drilling these holes. If we just go and drill these holes, we're not really guaranteed as well as we'd like the location of the hole. So best idea is to spot drill first, to use a real rigid spot drill. If you're using a stub drill or you're using a carbide drill or something that's pretty rigid, you can probably get away without doing the spot drilling, but it's good to learn how to do the spot drilling, so we're going to do it in this video. So first thing we do, it's real simple. We already made the spot drill, the 1/4 inch 90-degree spot drill tool in an earlier video. So you select tool paths, drill. Oh, and before I start that, I'm going to point something out that I've been doing poorly. You can't really tell what the heck each one of these paths is. So if I go in here and pick this one, I'm going to turn on the tool path so we can figure out what it is. Where's the, let's see, tool path. Okay, so this is the bottom bore. So we haven't been naming them, and just if you have to go edit later, this is just a nightmare. You can see that there's some logic, they're grouped up, but that doesn't really help you a whole lot. So parameters, to name it after the fact. Now the next one we're going to name before we're done. For some reason the comment is always in the it's in the tool. I don't know why it's in the tool, but this is where you name it. So I'm going to name this bottom bearing bore. And it's up to you to make a name that's sensible to you. Maybe you like abbreviations. It doesn't matter to me. I just want to show you where it goes. Say OK, and then when I close this down, you can now see bottom bearing bore, and this one is going to be the upper bearing bore. So let me turn off the tool path for first. The other thing you can do is you click on it once and you click on it second and wait, and you can just edit it directly here. So there's top bearing bore. So now we can tell these two apart, and really I should go back and fill all these in, but just to keep going on the video, I'm gonna go back to doing the spot drill. So here we're gonna pick tool paths, drill. And drilling is super easy here. You can use this, which is just go select anything, but that means I can select one of the problems here. I'm going to zoom in so you can see it better. One of the problems with this I can select anything idea is that I can grab, you see I can grab the circle, and right now it's highlighted to the center. That's great. That's exactly why I want to drill. But if I move, let's see, if I'm over here, look at that, I actually grabbed the corner. This is in a quadrant, so I guess I could do the same thing over here. So I can have a problem where right now I'm grabbing, I would be selecting on the circle, not in the center of the circle, and then if I move over to the side, I select the center of the circle, and that's just really easy to mess things up. So what I tend to do is I select entities, and then when you select the circle, it will understand the height and the center of the circle automatically. Makes things a lot easier. Because this is doing cam is not about getting it right once, it's about getting it right every time, over and over and over efficiently, so you can get your job done. So I'm gonna pick this circle, oops, and this circle, and you can see they're getting highlighted. Hopefully that picks up well after this thing is recorded. And so there I go, pick all the circles. Piece of cake. Oh. And then I'm going to go toolpath type, drill, which it was already selected. It doesn't show well until I click on it again, even though I can see here it's got a light gray selection. Tool, 1/4 inch spot drill, and it doesn't really matter. You got a 1/4 inch, 3/8, 1/2 inch spot drill. As long as it clears, it'll be fine. Holder, we're going to do the same Cat 40 ER32 that we've been using before. Cut parameters. I'm going to do a drill counter bore, and you can see this is what we want. We're going to do spot drills, just give me a dimple, and it'll be fine. Dwell, this is how long you actually spend at the bottom. It's probably a good idea to do a dwell. I just don't know how long of a dwell we should put in there. I think the ideal is you would do for a one fluted drill, you should be dwelling 1 revolution at least, so you don't end up having a chiseled feature at the bottom. I'm going to ignore it now, but I do want to point out where it is. Linking parameters, it's just like everything else, is super important. So I'm going to zoom in. Here's one instance where the center and the side don't matter because they're the same Z height. I select there. Top of stock, well, top of stock's right there. We don't want to spend all day going at a drill feed rate down. At this point, we've got everything featured except for the hole. So let's pick the top of the stock where it is, and then retract absolute. 0.1 is fine because we know that the top of the stock is 0, and that's another reason to have the top of the stock be at 0. Tip comp. Now, if we were drilling a through hole, which we will shortly, we want to understand the tip angle, and we want to make sure that we go through this amount here to get the. We don't just want to drill through and have the tip just dimple the edge, the other side. We want to get the drill all the way through. So we would let Mastercam understand the tip angle of our tool and the diameter, and calculate how far extra we have to go through. And then in addition to that, we'd have a breakthrough amount. But given that we are dimpling right now, just using a spot drill, we don't want to do that. Planes, it's right. Occasionally I'll do things between videos and I just want to make sure I have it right. So mill top is correct, and then of course coolant on, and say OK. And if we zoom out, you can see that the tool paths when you're drilling are real simple, as opposed to we've probably getting used to seeing all these really fancy intricate tool paths. So it's nice and simple. And I get, you know what, I forgot one thing really basic. We drilled to the surface. We didn't actually drill meaningfully. We didn't drill into the part. So the depth that I chose was the top of the part, and I totally boneheaded and forgot to drill the depth. So I'm going to drill 50 thou in. Now, there's some method to the madness here in how I'm drilling 50 thou in. If you have a 90-degree spot drill, the diameter is twice, and you haven't gotten to the body of the spot drill, you're still in the tip. The diameter that you drill, kind of the chamfer diameter, is twice the depth. So if I'm drilling 50 thou deep, I'm going to have a 100 thou diameter hole, and that should be good to catch the tip of the .201 drill that's going to follow. To do a really good job, typically you want to have a larger angle on the spot drill than on the drill, and in aluminum we're probably going to use a 118-degree spot drill. So 90 is not the best. We probably want a 135 or something bigger, but for cam purposes it doesn't really matter, and you really need to go and look at your tooling and make good decisions. Cam does not make you make good tooling decisions. It just allows you, it's a tool to use your tool efficiently. So if it's me, I'm probably looking for a 135 spot drill, 135-degree spot drill, so that 118-degree tool will center properly. Otherwise it's going to kind of bounce around that circle that it's gonna run into. But the cam is exactly the same, minus the tool creation and setting that angle. I'm gonna say OK. So I caught this error before I verified, but how would you catch it when you verified it? You'd run it and you'd say, whoa, I just ran my verify, and sure enough, I didn't see any cut happen. I saw the drill go all over the place, but nothing actually, I didn't get a dimple. So I just caught it in my head before it happened, but you can catch it. The whole point of verify is to catch that kind of stuff. So you can see I have the newly bored out STL model that I saved from last video, and I'm going to run this, and there you go. There is our spot drill. So this STL comparer, we're going to use that shortly, but not right now. So I'm going to get out of here, turn off the oh, and sure enough, I told you I was gonna label these cam operations, but I didn't. So spot drill 4/4 20s. So You need to name it something meaningful for yourself. That's good enough for me, but it may not make sense to you. So make sure you pick something that makes sense to you. So now we're starting to get these labels in here to help us understand what's what. Okay, so just another random lesson. We can select all operations, and we can select all dirty operations, and if there's no dirties, that's a good way to select none. So sometimes just getting used to these hotkeys up there can make things a little simpler for you. So one way to select all and select none really easily is to use these two. Even though technically you're selecting dirty operations, you shouldn't have dirty operations sitting around normally. Okay, so now let's do a cut and paste of this last one. Control C, Control V. Now, why are we cutting and pasting this? Because we are going to drill the 0.201 through holes that we just have done the spot drills, and that keeps us from having to go up here and fill things out. It's a very minor time savings, if any, but it's also good to see an alternate way to do things. So let's go into parameters, and now normally previously I've been rechaining everything, but we're going to do the exact same hole, so I don't need to rechain anything. Now you could go rechain, it's not going to hurt you, but thinking ahead's good, and trying to understand rather than just having rote memorization of the steps is definitely good. So now I'm going to change the comment first for the first time. Tap drill for 1/4 20 holes. And then we don't have a tool, so I'm going to select a tool, and there should be a 0.201 in there somewhere. So I need to go by diameters. I should filter it because I know exactly what I want. I want a drill. Is that a drill? No. Where is the drill? Is it here somewhere? That looks like a drill. That's a drill. So let's turn everything else off. I don't care about any of these other ones. A drill equal to 0.201. No, that's a 1/4 20. 1/4 20 tap drill. Okay, so we added that in there. It's and if we make sure these in order, you definitely don't want to have duplicate numbers here. That can cause all sorts of strangeness in Mastercam. It should take care of it for you, but it doesn't hurt to have look over the shoulder at it. Holder, we got that left over from last time. Cut parameter, pec drills make sense for a standard drill. And let's see, why are we, some reason we don't have those, the pec setup. Well, we'll take a look at that later. Now the linking parameters, the depth is, last time I selected this height and I subtracted 50 thousandths from it, and that was fine for the spot drill. But when we are doing a through hole, we know we're going to go to the back side, so we're going to click that. Top of stock is still in the same place. Now this is where we want tip comp. It knows that the number 7 drill is 118 degrees, and I'm going to say I want 50 thou breakthrough, but it's up to you. 10 thou is probably fine, but 50 thou is probably fine too. And then planes are okay, and let's turn on the coolant. Okay, and then we regen. Now if we, I'm going to select both of these guys, and then let's verify. We should see that first we tap drill, and now we do the through drilling. And so sure enough, it's not through, but that's because we have not machined the back side of the part away. So that looks okay. And then we need to cut these wheel stud holes. Those are going to be real simple. We're not going to drill them. We're going to, because they are, I believe, 5/8. Let me turn off these tool paths. I believe they're 5/8 inch holes. Let's actually go and let's measure those. So analyze entity property, and I'm going to wireframe it so I can choose the circle instead of the solid feature. And where's our diameter? Yep, 5/8. So we can Helix bore that with a 1/2 inch end mill. That's going to be a nice sturdy end mill, and it will do a great job. So I'll show you how to do that. It's really similar to drilling. It's not drilling, it's a different operation, but it's picked in a very similar way. So tool path, circle path. We could do circle mill or we could do helix bore. Their circle mill will cut in levels. I'm going to dramatize with the mouse. It will circle. It'll cut a circle. Well, it'll go into a lead in, do a circle, do a lead out, then go down, lead in, circle, lead out, and that works fine. Helix bore is another way where it kind of corkscrews its way in. And really, aside from picking the parameters for a circle mill and helix bore, they're just like drilling. So I'm going to pick a helix bore, and it's going to want to see drill point selection. This is just what we did earlier. Just like earlier, I want to use entities rather than features, because that keeps me from accidentally picking the side of a circle instead of the center. So I picked those 6. Okay, and we are going to helix bore. That's already chosen. Tool, we're going to use our 1/2" flat end mill. Pick our holder like we've done so many times before, Cat 40 or 32. Getting good at saying that. And then helix bore is like a contour, so we're going to see real similar things. So I'm going to use wear, nothing on the walls, rough finish. We're not going to have to worry about a rough finish in here. It's a 1/2" end mill and a 5/8 hole. It's not exactly taking the biggest cut in the world, so I'm going to not turn on a finish, though you absolutely could turn on a finish and you can change your parameters in there. When you're helixing, you do have to pick how far down you go each time. This is 80 thou. I'm going to leave the default because I don't know a better number right now, and I want to focus on the video. But definitely think about appropriate step down. That's a good place for machining calculators to help you out. And I'm going to go to link parameters. So depth is important to pick on this one. We're going to want to go pick the bottom. Now, I could have picked any of these features, but I just haven't looked at the bottom in so long that I wasn't sure, so I figured I'd take a look at the bottom. So there's the bottom. And where's the top of stock? Because we are fully machined except for this hole, so we know that this is the top of the stock right here. And if you see, the center is deep in there. So even though it looks like I'm picking the top, I'm actually picking something below. So be very, I'm going to give you an example of do what I do, not do what I say. I'm going to zoom in and actually be very careful about how I pick the top of the stock. Now I can see when I grab the circle, center's right here. That's good. And feed plane is a little higher. Actually, that feed plane, I want to be careful on that. I want to pick an absolute higher, because if Mastercam gets crazy and it decides to cut this circle and then this circle and it feeds, it's going to crash right through. That's no good. So I'm going to pick this as my feed plane plus 0.1, and that'll be good. Could have just thrown in 0.25, would have been fine. It would have gone up a little too high, but that's okay. But always be thinking about these 4 numbers and get a good understanding of what they are. If in doubt, experiment a bit. And they're not complicated numbers, but until you get used to them, they can seem a little daunting, but they're really not tough. And then coolant on, always on. Say OK. And then if we look very closely, you can see that we're helixing into through those holes. And I bet you we forgot to put a breakthrough on there. So let's go in here. And oh gosh, does this thing not have a breakthrough? Okay, so it doesn't have a breakthrough. Here's an example of, I really wish it had a breakthrough, but I'm not seeing one. Maybe I'm just looking over it. But easy enough to fix. Go into the depth, minus 0.05 at the end, do your math. I'll actually let Mastercam do the math, and there you go. Now you got a breakthrough of 50 thou. If you ever try to go figure out where this number from, it's going to be tough to figure out, but you can always just go select the bottom of that hole and subtract out 50 or 100. It'd be nice if it was separated, to have a separate breakthrough, but it's fine. Okay, and then we're going to clean that dirty operation. And how do I know I need that breakthrough? Well, it's just a matter of, those are the things that go through my head. that's really not a tough one to go fix after the fact in your machine if you need to get a deburrer out, but it's nice to get it right the first time, and just always be thinking about where you start, where you end up, the quality of all those cuts. So let's verify those last 3 operations, and there's our spot drill going around, and here's our drill, and here you go. You can see that we're helixing in for those 6 holes. Now the verified isn't really designed to be a great network television quality animation of what's going on. You can't see that that's a helix, but it's okay. It's the verify is very accurate. It just doesn't always you don't see nice neat helixes when it goes in. But I've had real good luck with it predicting surface finishes when you're doing weird 3D shapes and that sort of stuff, so don't get too concerned about that. Now we've finished the entire top of this part minus doing the boring, and so I'm going to save this as another STL file, which will be really critical for doing tooling for the other side. So save that, and then I'm going to do one more thing here. Really powerful feature that you can use in Cam is you can go and do File, Save Some, and I'm going to save an STL file of this solid. Now we already have a SolidWorks file of it, but I want an STL file, and you'll see shortly why I want an STL file. So I'm going to go not save this as an MCX. I'm going to save this as an STL, and I've already done it, but I'll save over it and say yes. Now why am I doing that? If I run a verify, and you've seen that another screen pop up at the end that may not be on yours, I have it defaulted on. Check compare to STL file, say OK, and then let's run our machine verify again, and we'll wait for it to helix away. What we're going to be doing is we're going to be comparing the actual machined simulation to the STL of the model. So if we made some error in machining depths or diameters, it'll show up when we do an STL compare. So it's already chosen because I've done this before the video, but let's say you just open up the little file drawer icon, pad slash solid, OK, and now you click this, which is compare the 2 files, and it'll show up in this heat map. Oops, oh, there you go, I did it wrong. Well, here's a good example of what not to do. I saved the STL incorrectly, so let's go fix that. Just computer's hung for a sec. Let's give it a minute to think about what it's done. I'm going to pause the video here while it thinks. Okay, and we're back here. And so what I did wrong, and I'm not sure why this is such a big limitation, but it is. This comes up. If you go into WCS, you always need to save your STLs with your CNTs in the top plane. Don't know why, but it's you need to do it. So let's do some save some again, and let's save as an STL. We just went through this. I want to replace that. Now we're gonna do. I don't have to put us back in the CNT of the mill top, but I'm gonna do it because otherwise I'll just forget and it'll come up again later. So I'm gonna verify this. Just to speed it up, I'm gonna change the moves per refresh. Just give it a minute to work through these helices. The helix boring is a little slow on verify. It's not too bad, so it's also a good reason to save your STL file so you don't have to wait for this stuff all the time. And let's compare. Okay, so this is really neat. This is a really, really neat feature I really like. You can see that the heat graph here, green is good, and it's telling us that we have no error, and then you can see the varying colors as we change. 1 thou of error will be yellow and 5 thou will be purple, and you can see we're perfect. We get some modeling errors here. 1 thou is actually the tolerance on the STL and a lot of the machining simulations, so 1 thou doesn't bother me at all. But oh, look at this, we have these huge blues in the bearing bores, and the reason we have those huge blue sections is we left 50 thou of stock on there for boring later. But having said all that, we're in pretty good shape. Now I'm trying to rotate it, and it's not, it barely rotates. So well, a big tip is, for some reason when you're doing the STL compares, it's super slow. So go back, if you want to rotate it, go and look at the verify, come over here, and come on, let's rotate. At some point it'll catch up. I can see my CPU's pegged right now between recording videos and trying to do CAD. It's a little rough on the computer. I'm gonna pause again while we wait for the computer to catch up. Okay, and I'm back. Some reason when you're doing STL compares, if you never start the STL compare, the computer's real fast, but once you do the STL compare, I think it's just brutal on memory and all sorts of other stuff, and sometimes it takes a while to come back. But if you want to rotate around, like I thought I saw something STL compare, but I couldn't rotate it to look at it. I thought I saw a problem here, and sure enough, that is a big old honkin' tootie problem. We can do an STL compare, and we can see that sure enough that thing is just gonna be blown out and all sorts of weird colors. There's red. Red is bad. So I'm gonna close this out, and that's the only error I saw that was egregious. And so that's, to me, that is very clearly, and just I was spinning around just to take a look, one extra hole. So somehow we chained an extra hole in there. So Helix bore, let's go to a peck drill for the tap drills, and 13 points. Sure enough, there's a point right there. So let's see if we can, let's see, there we go. It's point, not 3, point 2. We can see that little guy right there. So let's delete him, delete points. Okay, let's see, I don't think that worked. Delete points. Delete point 2. And for the life of me, I can't figure out how to do this. But we need to delete you. Oh, that's right, we need to go click on it. Delete that guy. He's out. Now we've got 12 points. Now we're going to rechain it. And I suspect since we copy and pasted above, we have the same problem here. We are going to just double check it's point 2. Sure enough, let's delete points. Delete that guy, he's out. Okay, rechain that. I don't want you to get the idea that this stuff is always flawless. It's super easy to make tiny mistakes, and you have to be very diligent about looking for them. If you don't look for them, don't look for mistakes, you're not going to find your mistakes until you cut them, and then you have $100 of aluminum vaporizer in front of your eyes as you put a hole in the wrong spot. So let's double check. There we go. And I want to go around and spin this guy so we can look at all these holes. And I've got one of these 3D mice. It's a 3D connection. I think it's made by Logitech. I think they bought the company that used to make this stuff, Space Pilot or something like that. Really like this thing. This is hard to do with the mouse, but you can do it pretty easily once you get the hand-eye of this thing. So that looks great. And we can do the STL compare, and looks good. Okay, that's excellent. So I'm going to close this guy out, and next video we'll talk about doing a boring operation down the middle of this guy, and we'll be completely done with the top of this, which will be fantastic.